In this video lesson, we are going to study the steps in nucleophilic substitution reactions of halogenoalkanes. But before we go ahead, what do you understand by a halogenoalkane? A halogenoalkane. A halogenoalkane, as the name implies, this is a compound in which one or more hydrogen atoms in an alkane have been replaced by a halogen atom. A compound in which one or more hydrogen atoms in an alkane have been replaced by a halogen atom. Yes, you know, when you see a halogen attached to an alkane, when you see a halogen attached to an alkane, that compound is a halogenoalkane. Remember, halogenoalkanes are classified as primary, secondary, and tertiary, depending on the alkyl groups attached to the carbon atom holding the halogen atom. I said halogenoalkanes are classified into primary, secondary, and tertiary halogenoalkane, depending on the number of alkyl groups attached to the carbon that is holding the halogen. Let me begin here by giving you this example. For instance, here, if you have a compound like this, let me give a compound like this one to. I have a compound like this one. That is a hydrogen. And you have bromine attached again. Now, the carbon atom holding the bromine, on the carbon atom holding the halogen, we have just one alkyl group there. This is an ethyl group that is attached there. In that case, we call this compound, this halogenoalkane is a primary halogenoalkane. We have a compound like this one. A compound like this one. The carbon atom, the carbon atom holding the halogen. The carbon atom holding the halogen atom has how many? Has one here and a two. The carbon atom holding the halogen has two methyl groups attached to it. So we call this a secondary halogenoalkane. Go further again. Here we have this. Here we have a carbon atom. The carbon atom holding the bromine has how many alkyl groups attached to it? It has 3 alkyl groups, and these alkyl groups are methyl groups. There are 3 methyl groups attached to the carbon atom holding the bromine. We have 1 here, we have 2, we have 3. In this case, we call this halogenoalkane a tertiary halogenoalkane. We can still write it in this way. This is we have okay. I name this primary halogenoalkane. I name this secondary halo and I also name this tertiary halogenoalkane. Okay. Now you have the 3 types of alkanes that are of halogenoalkanes that are there. We have the primary, we have the secondary, and we have the tertiary. And the nucleophilic substitution reaction of halogenoalkanes will depend whether it is a primary halogenoalkane, whether it is a tertiary halogenoalkane, or whether it's a secondary halogenoalkane, or whether it is a tertiary halogenoalkane. So in this case, the product and the mechanism of the reaction of this, the mechanism of the nucleophilic substitution will depend on the structure of the halogenoalkane. Primary halogenoalkanes, they have their own mechanism of reaction, their own mechanism of substitution. Then secondary halogenoalkane, they have their own mechanism of nucleophilic substitution. Meanwhile, the tertiary halogenoalkanes, they have their own nucleophilic substitution mechanism. Well, what do you understand by a nucleophile? In our previous video, we discussed issues on electrophile and nucleophile. But what is a nucleophile? Initially, we said a nucleophile is a species. It could be an ion or a molecule, which is attracted to a region of a negative charge. It is a species. It could be an ion or a molecule that is attracted to a region of positive charge. Because they are nucleophile, they are nucleus loving, they like moving towards electron deficient centers. They like moving or being attracted towards a species that are positively charged. In most cases, they carry a positive, a negative charge. In most cases, they carry a negative charge or a partial negative charge. And in some cases, they have a lone pair of electron. In most cases, all of them have lone pairs of electron because their aim of attacking a positive center, the aim of being attracted towards a positively charged species is to give what? Is to donate their pair of electron, because nucleophiles are electron pair donors. Nucleophiles are electron pair donors. We have species in nucleophiles. We have nucleophiles like example of nucleophiles are things like nucleophiles. We have nucleophiles. Example of nucleophile, we will have things like cyanide ion, the cyanide ion. We will also have hydroxide ion. We will also have ammonia molecule. I told you that molecule that have lone pairs of electron to give. Ammonium. We also have water that will have lone pair of electron to give, and many others. These are examples of nucleophile. This drives us to what we are going to study today: nucleophilic substitution. What is nucleophilic substitution? What is nucleophilic substitution? What is nucleophilic substitution? Nucleophilic substitution, as you hear it, nucleophilic substitution. Nucleophilic substitution, you can call it a nucleophilic substitution, that is SN, nucleophilic substitution. This is a mechanism in organic reaction. It's a mechanism in organic reaction in which a nucleophile attacks. Or we say a nucleophile is attracted to a carbon atom carrying a partial positive charge. Thereby doing what? Thereby substituting the carbon atom carrying a partial negative charge. Once more, for instance, I have, let me put it clear to you so that you can better understand. I have a reaction like this. I have a bond like this one. This is a bond. Of course, because of the electronegativity, the difference in electronegativity between carbon and the bromine, this one is going to have what? A partial positive charge, and this one is going to have a partial negative charge. And because of this, what happens? As I said, this is a mechanism in organic reaction in which a nucleophile attacks or is attracted to a carbon atom carrying a partial positive charge. A nucleophile is attracted to this end. Here, a nucleophile is attracted to this carbon atom carrying what? A partial positive charge. So when a nucleophile, let me say a nucleophile, this is it here. Now a nucleophile is a nucleophile. As I said, a nucleophile, they always have lone pairs of electron, and they carry a negative charge. So now this electrophile is doing what? It is attracted, or it attacks a carbon atom carrying a partial positive charge. By doing what? It does this. The nucleophile is attracted here to the carbon atom carrying a partial positive charge. What happens as the nucleophile is approaching the carbon atom carrying the partial positive charge? Remember the carbon-bromine bond. There is a pair of electrons here. As the nucleophile is approaching this carbon atom carrying a partial positive charge, what happens? Electrons here in this bond are doing what? Are repelled towards bromine. Electrons here are repelled towards bromine. And when they are repelled towards bromine, what happens? It results in a heterolytic fission with bromine taking all the electrons. That's what happens. When a nucleophile attacks the carbon atom carrying the partial positive charge, or when a nucleophile is attracted to the carbon atom carrying the carbon atom carrying the partial positive charge, what happens at that particular moment? Electrons in the nucleophile are doing what? They are repelling the bonding electrons here in the carbon-bromine bond. So electrons are repelled and are pushed towards the bromine. And this results in what? Heterolytic fission, with bromine doing what? Bromine ending up with what? The bromide ion ending up with the lone pair of electrons. And the bond does what? The bond splits. So the curly arrow are indicating the movement of what? Movement of the lone pair of electrons on the nucleophile. And here they are also indicating the movement of the bonding electrons here to bromine. So this bromine, the bromide ion that finally cuts off from this carbon-bromine bond is what we call the leaving group. So that is what we call electrophilic substitution. So when it attaches itself here, when the nucleophile attacks the carbon atom having the partial positive charge, it is doing what? At that particular time that is attacking this carbon atom carrying the partial positive charge, as it is repelling the electrons, it is donating this lone pair of electrons here to the carbon. And as it is donating the lone pair of electrons to the carbon, because bromine has taken away the other the bonding electron, so it has to donate this electron here. And by doing that, it does what? It is using that same bond to form a bond. It is using that same lone pair of electron to form a bond between the carbon and the nucleophile. And what result will be this one? It will be carbon, and the nucleophile takes the position. And that nucleophile automatically takes the position of what? Of the bromide ion. So the bromide ion, which we call the leaving group, will do what? Will remain there. So that's what we call nucleophilic substitution. That is the mechanism going on in nucleophilic substitution. Again, it should be remembered that halogenoalkanes undergo many nucleophilic substitution reaction. Halogenoalkanes undergo many nucleophilic substitution reaction. As they undergo this nucleophilic substitution, the mechanism in which this substitution takes place, there are two mechanisms in which this substitution reaction takes place. We have the SN1 mechanism and the SN2 mechanism. SN1 and SN2. SN1 and SN2 mechanism. What do you understand by an SN1 and SN2 mechanism? SN1 mechanism and SN2 mechanism, these are two different mechanisms. This mechanism, SN1 mechanism, will go will go depending on the structure of the halogenoalkane. SN2 mechanism will also go depending on the structure of the halogenoalkane. Summarizingly, I am saying, learners, if you are given a question and you are asked, what mechanism would this reaction undergo? The first thing is you need to look at the structure of the halogenoalkane, whether it is a primary, it is a secondary, or it is a tertiary. Depending on the structure of the halogenoalkane, you will now determine whether it undergoes as a SN1 mechanism or a SN2 mechanism. Let's start with SN1 mechanism. SN1 reaction mechanism in halogenoalkanes. What is SN1 mechanism? The first thing about S stands for substitution. S is equals to substitution. S stands for substitution, and the N stands to nucleophilic. Then 1 indicates the number of reacting species. So when we say SN1, SN, we are referring to what? Nucleophilic. We mean that you can call it nucleophilic substitution unimolecular. Nucleophilic substitution unimolecular. Unimolecular, I am saying unimolecular because there is only one. Unimolecular means it's only one molecule, it's only one reactant, it's only one reacting species that is involved in the rate determining step. So N stands for nucleophilic, S stands for substitution, unimolecular stands for what? Unimolecular stands for the number of only one reacting species or only one reactant that is involved in the rate determining step. If it was SN2, we will say it is nucleophilic substitution bimolecular. The one here, once more, indicates the number of reacting species at the rate determining step. SN1 indicates that only one reacting species is involved at the rate determining step. SN2 indicates that there are two reacting species involved at the rate determining step. The rate determining step is the slowest step. That is the slow step in a reaction. So now SN1. What is SN1? We have said it. It is nucleophilic substitution unimolecular. And what happens in SN1? What are the molecules? What is the type of the type of halogenoalkane involved in SN1 mechanism? And how does it happen? The first thing is the type of halogenoalkane involved in an SN1 mechanism is that it is only tertiary halogenoalkanes. Only tertiary halogenoalkanes are involved in SN1 mechanism. I showed you an example of a tertiary halogenoalkane. I said tertiary halogenoalkane. That is when the carbon atom holding the halogen has how many? It has 3 other alkyl groups. In this case, there are 3 methyl groups attached to the carbon holding the bromine. So this compound here is a tertiary halogenoalkane. And this compound here will undergo an SN1 mechanism that we are going to discuss. So now, in SN1 mechanism, this involves only tertiary halogenoalkanes. What happens? Since it is SN1, as the name implies, only one reactant, only one reacting species is involved in the rate determining step. And that species that is really reacting there is the halide. Only one reacting species, that's the halide, the halogen, that is involved in it. For that reason, we say it is involved in it. And for that reason, we say it is an SN1 mechanism. So now, there is heterolytic in this mechanism. In this mechanism, it is a two-step mechanism. It is a two-step mechanism where initially there is when the nucleophile approaches, excuse me, it is a two-step mechanism. The first step is ionization. That is the heterolytic bond breaking with the halide leaving, resulting in a carbocation. And this is followed by what? Followed by bond formation with the nucleophile. That is a nucleophilic attack. Our example here we'll be using the example of substitution with hydroxide ion. So the halogenoalkane that we'll be using is 2-bromo, 2-methyl propane, and the sodium hydroxide, and the aqueous ethanol. Those are the reagents. 2-bromo, 2-methyl propane, sodium hydroxide, and aqueous ethanol. So the substitution will be what? It will be the hydroxide that will be substituting the bromine. So what happens here is that this mixture is heated. It is heated under reflux, and eventually the OH, or what we call the hydroxide ion, now substitute the bromine, and a new product is formed. And this product will be what? The product is 2-methyl propan-2-ol. 2-methyl propan-2-ol. Okay, this is the mechanism. Step number 1 in this mechanism. This is step number 1. Step 1. Step 1. In step 1, I said step 1, ionization of the carbon-bromine bond. That is step 1. Ionization of the carbon bromine bond. That is step number 1. How does the ionization of carbon bromine bond occurs? This is the structure. Let me just draw it. You see it. Let me draw it, and you see how it goes. H3 carbon. This carbon. It should be noticed that the carbon bromine bond is polar because of the different electronegativity, as I explained to you. This bond is polar. So it is polar. So let me this will result in this is a slow step, and it's a reversible reaction resulting in, it's a slow step and a reversible reaction resulting in a carbocation. A carbocation is formed here. This is a carbocation. The bromide leaves them. The bromide is the leaving group. So what happens here? This step is slow. This is a slow step. There's a slow step. So what is happening here? As I told you initially, this should be explained using the curly arrows. Because of the electronegativity here, what is happening here? There's electronegativity. This one has a higher electronegativity than the carbon. So electrons, it has that tendency to draw electron towards itself. Electrons will move towards this one. Now it's a slow process. Ionization takes place. A carbocation is formed, and the bromide leaves with a pair of electrons. So this one is lack of electron. That is why you have a positive charge here. Bromide has excess electron. That's why you have a negative charge here. Now, I said the bond is polar. The bond does what? There is, because of this different electronegativity, this result in what? It result in heterolytic fission. This carbon bromine bond breaks heterolytically, forming a carbocation, while the bromide leaves with a pair of electrons. That is what happens. Step number two takes us to step 2. Step number 2. Step number 2, we call it nucleophilic attack. Nucleophilic attack. The nucleophile now attacks. Remember that the carbocation that has been formed here is very, very reactive. What happens? There will be a nucleophilic attack. And we said we are substituting using what? We are substituting this using our hydroxide. Substitution with hydroxide ion. That comes from what? That comes from the from sodium hydroxide. When sodium hydroxide ionizes in water, what happens? It gives a hydroxide ion. That hydroxide is the one that is going to substitute. It is acting as a nucleophile. It's acting as a nucleophile because it has a lone pair. It has a lone pair of electron on the oxygen. So this is what happens. Now let me draw the structure again for you to better understand. You will have here. You have This is our nucleophile. That is our nucleophile. So the product that results here will be here will be this one. So now, and this step is what? This step is a fast, is very fast, because there's rapid attack of the nucleophile. The nucleophile attacks the carbocation rapidly. So now, see what is happening. The nucleophile, immediately the carbocation is formed. Immediately this carbocation is formed, what happens? The nucleophile, which is the hydroxide ion, attacks it, thereby donating what? Donating the lone pair of electron, here to what? Donating its lone pair of electron to what? To the positive carbon. As it is donating the lone pair of electron to the positive carbon, it is doing what? It is now forming a new covalent bond between carbon and oxygen here. A new covalent bond is now formed between carbon and the OH. And this is indicated by what? By the curly arrows. See how the curly arrow goes. From what? From the lone pair of electron to the positive carbon. The first step, I said this was step number 1, ionization. Ionization of the carbon-bromine bond. And I said the carbon-bromine bond is polar. For that purpose, bromine draws all electrons towards itself. And because of it, this is a slow reaction. And within this reaction, it is slow. Because the person acting here mostly is this species, the bromine, is the one acting here. Is the only person that is acting here. Bromine is the only person who is really acting here. In doing that, what happens? There is heterolytic fission. Bromine now goes with what? With the lone pair of electron. The bonding electron that were here have been carried by the bromide. And now what? The carbon, which is now positively charged, is now locked with no 2 electrons. So because of it, this carbon is very, very reactive. And because it is reactive, any nucleophile around itself does what? Will be attracted to it. Now, the nucleophile here, which is the hydroxide, now attacks the positive carbon. As the OH is attracted towards the positive carbon, it does what? It donates this pair of electron to this positive carbon. Now, a new bond is established. And this reaction is very fast to form an OH. And this results in an alcohol. And this alcohol is what? We have this is one. This is the first carbon, second carbon, and the third carbon. We now say it is 2-methyl. This is 2-methyl. What? 2-methyl propan. 1, 2, 3 propan. 2 all. There is one. This is one carbon. Let me number the carbon so that you can see. Carbon 1, carbon 2, carbon 3. carbon 1, carbon 2, carbon 3. You can still start from here. Carbon 1, carbon 2, and carbon 3 up. So now, okay, OH is located on the second carbon. There's a methyl group that is also located on the second carbon. We now say 2-methyl propan 1, 2, 3. Propan 2-ol. So that is the name of our product. 2-methyl propan 2-ol is the name of our product. This reaction could be summarized in this form. In the exam, the examiner will give a reaction like this as a summary. That's what the examiner will give you. I've mainly explained the steps, but the examiner gives you a straight chain reaction. This is the first step, the rate determining step, and which is very slow, and this is the last step. So learners, once more, know the movement of the curly arrows. Bromine is highly electronegative. It takes all the 2 electrons. A carbocation is formed. This is a tertiary carbocation. It has the carbocation that was having, the carbon that was having the bromine is doing what? It's having 3 alkyl groups or 3 methyl groups attached to it. So this is a summary of the mechanism. Our second example will be a substitution with cyanide ion. Substitution with cyanide ion. That will be our second example. Substitution with cyanide ion. Substitution with cyanide ion. It is the same thing, the same mechanism. It's the same mechanism. We are going to use the same tertiary halogenoalkane in this one. But it should be noted that in this reaction, when a tertiary halogenoalkane is heated under reflux with cyanide ion in ethanol, the cyanide will now do what? The cyanide will substitute the halogen to form the nitrile. This reaction is very important because it leads to the formation of another organic compound. We call them the nitriles. An organic compound results from this reaction involving potassium cyanide. A new organic compound will result from it because of the presence of the nitrogen. So we use cyanide to form another new compound. So substituting with the cyanide ion, I said when a tertiary halogenoalkane is heated under reflux with cyanide ion in ethanol, the cyanide will now do what? The cyanide, which is acting as a nucleophile, will substitute the halogen to form a nitrile. For instance, ethanolic potassium cyanide, which ethanolic potassium cyanide, which is already here, is heated with what? Is heated, I say we want to use the other example, is heated with 2-bromo-2-methyl propane under reflux. The bromine is substituted by the what? By the cyanide. Okay, let me use that example and let's see if cyanide, let me say this one. This reaction here, if we heat this, if this tertiary halogenoalkane is heated with ethanolic potassium cyanide, what happens under reflux? What happens? A nitrile is formed. A nitrile is formed. This can be represented in an ionic form in this form. In ionic form, Ionically, the equation can be like this. Ionically, we can have it like this. The equation can be in this form. We have two, that is 2 bromo 2 methyl propane, B arrow plus, in solution, what happens? This would dissociate to give a cyanide ion, and the cyanide ion does what? It attaches itself here. This is how you can get it. The cyanide ion attaches itself here, and the bromide will be left. And the bromide ion will be left. So now, I want us to still write it the way we did the other one. 2 bromo 2 methyl propane. Step 1. In step 1, I said ionization of the CB arrow. Ionization of the CB arrow bond. Ionization of the CB arrow bond. And how does it go? It goes like this. I have 2 methyl I said this is a slow step. This is a slow step. And I told you that this bond is a polar bond, where we have this. And in that case, for an ionization to occur, that's what is happening there. So that is what you see. That is what is happening there. Step number 2 will be what? Rapid attack by the cyanide. Rapid attack by the cyanide. Step 2. Step 2. Rapid attack by the nucleophile cyanide. By the cyanide ion. Yeah. Rapid attack by the cyanide ion. And this is how it is happening. The carbocation, the first step is ionization. This ionization does what? Leads to ionization is by heterolytic fission. The bromide goes with a lone pair of electron. A carbocation is formed. Now the second step is what? Because the carbocation is highly reactive, the cyanide now attacks the carbocation, donating a pair of electrons and forming a new bond with the carbon. And this is what is happening. We have The carbocation is here. I said this is a very fast step. The step is very fast. So this is how the attack goes. There's an attack there. It's very fast, resulting in this, to form this. So step 2, the rapid attack by the cyanide ion. Because the carbocation is highly reactive, the cyanide ion, which is our electrophile, which is our nucleophile, is attracted to the positive carbon, donating electrons, and a new covalent bond is formed here. This new covalent bond is formed here. And the name of this new covalent bond, this bond here, is what we call it is. This one here, it is 2,2-dimethyl propane nitrile. 2,2-dimethyl propane nitrile. 2,2-dimethyl dimethyl propane nitrile. Propane nitrile. It's a new organic compound that is being formed. So this new organic compound, you will see that initially we had, but you see we now have 1, 2, 3, 4, 5, 5 carbon atoms here. Meanwhile, in the initial compound, we had just 1, 2, 3, 4. So the very important thing here is that this leads to the formation of a nitrile. It leads to the formation of a nitrile, and this reaction can be represented in this form. I can summarize the reaction in this form. This is how we can summarize the reaction. To give This is a fast reaction. This is fast. This is a slow reaction. I told you about the polarity of the bond. So you see from here, it goes there. There's nucleophilic attack. There is nucleophilic attack here. The arrow is showing the nucleophilic attack from the there's nucleophilic attack there. So you now see that this is a summary. The summary of the reaction where the tertiary halogenoalkane does what? Ionization. The first step is ionization. It is a slow process leading to what? Ionization leading to the formation of a bromide. A bromide now goes, of course, put there here. The bromide now leaves. So this is just a summary of it. Ionization leads to what? The formation of a carbocation. Now, a cyanide does what? Attacks, a nucleophilic attack here, attacks the positive charge carbon. And what? There's rapid attack here. That's why the reaction is very fast. A new bond is formed between, let me put it this way, a different color. A new bond is formed between carbon and cyanide. So that's why we call it 2,2-dimethyl propane nitrile. 2,2-dimethyl. So we say 2,2-dimethyl propane nitrile is, this is how we are naming it. This is carbon 1. This is carbon from here. Because nitrile is the functional group. We say it is, this is 1, this is 2, and this is 3. Now, the two methyl groups are there. We say 2,2-dimethyl propane nitrile. Okay. Now, our learners, I want you to have some tips on this SN1 mechanism. I want you to have some tips on this SN1 mechanism. Some tips on this SN1 mechanism I would like you to understand. The first one is tips to remember. Number 1, I said tertiary halogenoalkanes cannot undergo SN2 mechanism. The reason why tertiary halogenoalkane cannot undergo SN2 mechanism is because the tertiary halogenoalkanes, the opposite end of the halogen is bulky. 1. Opposite end of the halogen is bulky. Is bulky or clustered with alkyl groups. The opposite end of the halogen is the opposite end of the halogen is bulky. Is bulky, or you can say it is clustered. with alkyl groups. When there are many alkyl groups, what happens? They help to prevent the nucleophile from attacking from the opposite end. For instance, here, I said the opposite end. The opposite end, this is the bromine. The opposite end here, it is bulky or it is clustered with many methyl groups. For that reason, there's no space here. So it helps to prevent the nucleophile from attacking from this end. For that reason, they cannot undergo SN2, because SN2 mechanism, the nucleophile attacks from behind. So this one, the nucleophile cannot attack from behind because the opposite end of the halogen here is clustered, is bulky, and prevent the attack of the nucleophile. Point number two. Point number two. The inductive effect of the alkyl groups attached to the carbon holding the halogen helps to reduce the charge density. It helps to reduce the charge density and make the molecule more stable. Inductive effect. Inductive effect of tertiary halogenoalkane. This one is more stable. It is more stable. So now, look at this one again here. The inductive effect. I said in this molecule, here we have 1, 2, 3. There are 3 alkyl groups or methyl group attached to this carbon holding the halogen. What does it imply? The methyl groups, they have inductive effects. They are electron donating onto this carbon, onto this positive carbon. They are helping to donate electrons, pushing electrons from themselves into the positive carbon, thereby reducing the charge density, on this carbon, on the positive carbon, and making this compound to be more stable. And when it is more stable, yeah, it cannot undergo SN2. So now, there are 2 reasons. The opposite side is bulky. The opposite side of the halogen is bulky. Secondly, the high inductive effect of the tertiary halogenoalkane. Then, secondly, secondary halogenoalkane can react by SN1 or SN2. Secondary halogenoalkane, they can either react by SN1 mechanism or by SN2 mechanism. Why do I say they can react by SN1 or by SN2? Because the opposite end of a secondary halogenoalkane is not clustered. Just as in primary halogenoalkane, the secondary halogenoalkane, the opposite side of the halogen is not clustered. For that reason, a nucleophile can attack from behind. A nucleophile can attack from the opposite end. The second reason is this. Secondary carbocation formed are more stable in secondary halogenoalkane. I said the secondary carbocation that is formed in a secondary halogenoalkane is more stable than the one that is formed in primary carbocation. For that reason, a secondary halogenoalkane can react by SN1 and also by SN2. Thank you, learners. Watch the video on SN2 mechanism. Thank you once more. Like, share, and most importantly, subscribe so that our videos that will be coming up, you'll be the first to receive them.